So we're going to check the door if you have any minutes. So any questions so far? Or anything you want? Then take it.
How many of you would raise their hand if I say second order Taylor expansion is cool? Okay. This is kind of lame because all right. Sorry. We're going to talk today about neural architecture search. Well, it's kind of like, because you're giving up on a sunny day, I just added a lot of slides, so a lot of content, so you're really be happy about this presentation. Uh, 2011, I finished. Yeah, that means I'm Iranian. I did my master's in an Erasmus program in Finland and it was a complete different field, Java, Apache Storm, completely different, decision tree. I worked at Gapminder Foundation. This is my Twitter. I don't tweet about like my shoes and stuff. I usually tweet about data science and data science solutions, and they're already building up, be more active in the AI stuff. Presentation. I'm going to do 3 papers in one presentation. It's going to be a lot. Initially, I wanted to just talk about implementation of how you can actually implement it, but then it kind of gets very hard to follow because it would just be like, you guys didn't get. We're going to talk about neural architecture search, which was the first paper 2 years ago about using reinforcement learning to create neural nets. Then we're going to talk about a very important architecture search with parameter shading that was actually accepted ICML 2018. And then conclusions, discussions, and stuff like that. Before any talk, I always think about like, what is it that I expect people to understand from this talk? Spanish. So think about intuitions, not very detailed, not very up, kind of in the middle, trying to make sense of what I've said. If I say something really but if you had more like discussions and stuff like that, we will take it at the end. So let's go with introduction. I really like this picture specifically. Top. Have the multi-armed bandits. Let's say you're really like puzzled with gambling. Let's say you're not addicted to gambling. Puzzled. You have a slot machine, and then you have typical multi-armed bandit. So you have an action and a reward. Then let's say you have 2 of these machines. Then something changes. You're going to have a state. Hardcore reinforcement learning problems, they're really complicated because with a machine, you get instant reward. When you're walking in a maze and you make a left, you don't know if actually that making a left actually will help you to finish the maze or not. So always the reward is delayed. So like reinforcement learning researchers, like top-notch researchers, they always are only interested in type of problems that has delayed reward. That's like our world, basically. Network type of problem. We're going to talk about something condition is important because in this setting, your reward is always the last reward you got. can make an associated reinforcement learning. So this is a typical reinforcement learning. You have an the expectancy of the probability of making a decision times the reward it comes. Then you know that the reward is not differentiable. You change it to a probability of the conditional actions you're making. Thank you. And then from there, you actually go to Monte Carlo. And that T there is the number of things you need to predict for your neural network. The problem with this actually forgot to say, came up with this. A lot of courses in reinforcement learning, not Silver, but a lot of them don't cover this reinforcement algorithm actually. So the problem with this is that it has a lot of variance. It's an unbiased estimate, but it has a lot of variance. Why? Because you don't look at a lot of samples, you pick one and it's noisy. So what you do is that you add this B here, the baseline, to actually try to reduce this variance of your data, rewards you're getting. And this baseline is actually a very baseline. Usually they do it with exponential moving averages. But then that's also a complicated problem. Spain is NAS, they call it neural architecture search. And train it, and whenever accuracy is high, treat that as a reward, so that you're hoping that in a reinforcement learning setting, you're going to assign and find models that connect you to the highest reward. That's the essence of neural architecture search. It sounds simple, but it's not that simple. And what is this different? How is this different from a hyperparameter optimization research? It's been done since 2000, really. A lot of good work. James Berger's stuff, the one that actually came up with HyperOpt, the algorithm and also the code behind HyperOpt. What is this different from that type of things we had in hyperparameter optimization? Is that the configuration space is dynamic. So you can actually build a lot of dynamic. This is a quote by the paper. I'm not saying I agree with this, but this is a code why is it so different than hyperparameter optimization? Why is it so much cooler? It's because, it's dynamic, so you don't have to treat it like a static problem. In case, in this study, in this paper, they limit the search space because, you cannot go all over the space. It's exponentially expensive. So, for example, they have this RNN controller to have the filter height between 1 and 7 only odd numbers, and the width the same. And they perform different experiments, and some of which they turn it off, they turn it on, try to see what works best. If I pause here, in parentheses, you just realize that you actually had to fixate this space. So going back to the previous slide, I'm not sure how dynamic this whole system is. When you're reading the papers, you always if you just listen to the author, then you're gonna feel oh my God, he's Einstein. But you have to at some point stand there and say, what did you just say? This is one of the problems. So actually you have to have a fixed state, because then it's super expensive. And let's talk about the controller, that RNN, that LSTM. The RNN LSTM, first and foremost, all these 3 papers, they're written a stream of consciousness style. The authors are just talking about everything in each section, so it's hard to actually pick this up. So I'm not going to talk. It has 35 hidden units, and it's trained with Adam. And they have this idea in this paper, the first paper, that you want to make this parallel. So you have different search rewards, they send it back to the search. They have shards and stuff. They're talking about how many shards they have. It's a huge, huge shard to actually run this. And what does this NAS do? What is this controller trying to do? It's literally a 5-step process, and it gets repeated in different depths. So what it does is that it picks it picks a hidden state, actually 2, and then it samples 2 hidden states. Another 2 hidden states, it picks an operation, like an activation on those, and then it samples another activation to marry them together, and it does it in a loop. It's something like this. So if you look at it, of blurry. So it's an auto-regressive, you know, the output from this layer is going to the next one. And you select one hidden. Think of it that you're creating a cell, right? A cell in a neural network. So what you do is that you pick a hidden state, you pick your second one, you pick an operation, and you do the third one. So it's really blurry. So these are the hidden layers that maybe it's in the middle of the neural network, maybe it's not at the front or at the end. Now, this is very confusing at this stage, probably for all of you, but it will be better because all three papers kind of touch upon that and build on this. And this is the servers. Like, it's all, again, blurry, but I can read to you. Like, you have the parameter servers, and then you have the controller, different servers, and they're all running the replicas. So each one of these is training one neural network and reports the reward. Yeah, this first study was 2016. It's like a huge, if you know, like, it's like a huge operation now, because you're just like training. I mean, you train one deep learning model, it takes forever. Imagine they're running thousands of thousands all the time. This might actually be better in terms of like explaining what they're trying to do. I forgot to mention that neural architecture search works both on CNNs and RNNs. So it's kind of like a general purpose framework that you can run. So if you look at this, for example, this is what they call like a hidden state. So I'll try to read this. I don't know. Can you see this in the back? Yeah. Good for me. Yeah. So this has a weight. This has a weight. So you're trying to make this dynamically with an RNN. That's what you're trying to do. And then here you have element quantification. This is for cell number 0, cell number 1, and these are more operations that you're sampling in the setting. And then here, this is kind of tricky because then you have to connect something to or not. So when you sample that, if it's 0, you connect it to cell number 0, and if it's 1, you connect it to cell number 1. And in this case, you only have 3 cells in total. So I'm pretty sure so far you're just confused because it takes forever. You have, so it's a string. So encoder it receives a string, okay? And the strings are operations. So 2. So this is what you get as an encoder and what you get as an decoder. It changes in the next model, the way it samples here. It will be more. I started with the pictures because now I'm going to talk about more details. It's going to be more. Yeah, you have. So they have. So this state has like convolutional layer, like with the kernel 3, 3, 5, 5. They have a list in the paper. So like typical normal. I think you also missed one of the slides. So they have like, okay, filter between 1 and 7. So basically every one of them is a cell. But I think that the confusing part here is that the second paper they publish, they explain why they're trying to do this. Is it good enough? I see something in your eyes like. Yes, where you get it. It's a reinforcement setting. So you're actually trying to you start with an initialization. You start with a random initialization, right? Because you don't have a network yet, right? You can't run gradient descent. So what you do is that you give the network a set of initialization, and it gives you a reward, right? And then from there, with policy gradient, you go to a better reward. Yes. And the possible actions described by probability. Yes. A softmax. Yes. Right. And on the top output layer, that is the probability for the action and action which operates. Yes. Right. Plus where to connect them. because you also want to know where do you want to connect this cell. So you have two outputs.
Question, but so you're optimizing the structure of your neural network, but then in order to evaluate whether or not what's the reward for that neural network, I'm guessing you're using a training data.
No accuracy evaluation.
But
You're
then
using the accuracy evaluation.
But you need a data set, right?
Yeah.
And then does that mean that you are optimizing an architecture for a training data?
Well, for many of them, right? So the data is constant. Let's say you have C410. They use C410. You have the C410 data, right? You don't have an architecture. You start sampling based on reinforcement. Okay? You get something, anything. Just think of a random network. You get a reward, right? Then you put that reward in the reinforced algorithm, and then your data is the same. You change the architecture to find something that fits CFAR. And you use that so they don't use the whole data. Good enough? I hope I'm not over time. Okay, so yeah, this is also, I'm just trying to say that they also do it for CNNs. I showed it for the RNN. RNN is much more complicated, but they also do it with CNNs. And so because they actually, when they're sampling, let's say they sample and some nodes never get connected to anything. They're not in the sample. So they have this like failover approach that say, okay, let's assume that like if a layer is not connected to any input, we put it like, it's a hack basically, trying to like make sense of the whole like sampling process. So we say if the layer is not connected to any input layer, we connect it to the image or like the input layer of the whole framework. And then in the final layer, for example, if we see that there are nodes there, then we average everything and put them into the output. So because they have to make sure that every node is connected somehow. And they actually are able to, I skipped this one. They actually form skip connections because they put this anchor, and you can't read this, but it's an anchor point. So they're able to actually learn that they can skip connections between cells. It's on 800 GPUs. And it takes like some days, 24 days. I don't remember actually. So it's not possible to use this approach if you're on the start. I think 24 days. They actually get the state of the art for CFAR, which is a great achievement. That leads us to the second paper. So it's impossible. Like, even I think it was mid-2017, this paper was published, and it was a good idea. Like, it's nice to formulate this problem as an enforcement line, but if you like that, it's like no one's reproduced this. Like, you can't do this. So then Barrett Zoff, who is part of the Google Brain, he's really focused on this problem. So he takes like this to the next level. So he writes this learning transferable architecture for scalable image recognition paper, which is a really nice paper. I highly recommend reading it. What he says, like, this is horrible. Like, I can't even read this. So what he says is that instead of learning the whole architecture, let's create building blocks. Let's learn a best convolutional cell and use that. So let's say you have an ImageNet problem and you want to find the best architecture on ImageNet. Take something simpler like CFAR, try to optimize for a cell, for a convolutional cell, and take that cell and reproduce that cell and just learn the weights. So you're going to have identical cells in the whole network. So he has this hunch that this is going to work, and he shows that it does work. So what he does, I don't know why I can't see this yet. Anyhow. So when we call this NASNet search space, and then when he said, I just said it to you, basically limit the search space to time. Whoa. Is it better? Oh. Good stuff. So yeah, so he has this hunch that this is going to work. When I read the paper, I was like, this is nuts. Like one cell, I was like, this is nuts. And actually, it's not only faster, it's really expensive, and he actually shows that this works better. So he embeds this idea back to the NAS, but then he doesn't really go further. And that leads us to the third paper that was just like got a lot of attention in the media, and yeah. So I was stupid enough to read the third paper by now. So it's a marriage of the first one and the second one. How do you make this more efficient? Okay, so what they do is that what if in the previous work that we've had with neural architecture search, we learn a cell so that we actually use that cell and try to transfer knowledge to the bigger network. This time it's not running it on CFAR and then replicate it on ImageNet. This time it's only CFAR. So you learn a small set on CFAR, for example, and then you replicate that on CFAR again so that you hope that it works actually. There are a couple of chairs here as well. So in this case, ENAS, they call it efficient neural architecture search. ENAS has like two search space, a micro and micro and a macro. So in the micro one, you learn a cell, and in the macro search, you actually try to learn only the weights from that cell. One of the things that they introduce in this study is that they say there are two types of convolutional cells. One of them called normal cells. They're the types that you run a feature map and the size doesn't change. And the other type is like a reduction cell, where you like max pooling, you actually decrease or increase. You never actually increase, but you decrease the cell. So they actually learn them differently in the algorithm. So in the training, just like the first one, you have two, actually not like the first one, you have one step further. You actually learn, when you don't have your network, you sample it to learn one cell only. So you optimize for just the cell on the limited data. And when you learn that cell, you actually learn the different structures of that cell that can be generated to optimize CFAR. And then you use the reward. The reward is the validation set accuracy that you're using during training. And you're trying to learn. One of the most interesting things in this paper that you read here is that they say that if you have one estimate of the policy gradient, if you train one network, that's enough. In the previous studies, they always use 10 and 12. And they say it works, but it doesn't work. Even when they submitted the paper to ICML, everybody commented that it's insane to assume that one estimate of policy gradient is going to get you good enough convergence. I myself used 1, doesn't work. I used 3, doesn't work. Someone used 12. I haven't used 12 because it takes 5 days to train. So I haven't used 12, but it looks like that if you use 12, for each estimate you average over 12 networks, then you get a good one in convergence. I'll talk about what my experience with this, and even this is horrible. I can't read it myself. So this is the same thing. That does not show anything. But this literally looks the same. And what they mean by this is that when you have the cells ready, and if you don't change the number of cells, they use 12. You actually just basically have a subgraph. You don't really learn something new. You can just turn it on and off. So that's kind of like transfer learning in this way. More stuff.
So do you think that we get about the transfer learning? What type of this transfer learning here?
Because you learn a cell, and in the second training, you just use the cell because you learn one cell. So what you care about is how this cell is, how multiple n times of this cell are connected. Do I make sense?
That's the n times.
Yeah, n times. So they actually set a limit for saying, okay, imagine we have 20 of these best cells we have. So it's kind of a transfer learning because you're learning something, a module, and then you apply it on the second training phase.
And so always the same data set.
Yeah, that's what I said, but that's why I put the code. It doesn't make sense. But they mention it. Yeah, this is the same thing for the convolution of them.
When you say cell, what is
It's a mini network. Think of it as mini network. It can be whatever. In different data sets, they show that it could have from input to output layer everything. So imagine you actually have a common set of like components or operations that you can embed and just like have that 10 times and make a network out of that. That is a cell, but that doesn't mean one operation. It means a mixture of operations. In their study, it's 6 actually. And this is the result. It's one of those papers that is really like, I'm beating the benchmark type of attitude. Like, oh, I got like 2% more, like blah, blah, blah. If you read all this that you can, I even can. This part is ENAS. And they show that you actually can get less of the depth with the best, with the state-of-the-art networks. You can actually have more compact networks this way. And this is ENAS, and they show some of the old stuff, that like Armani stuff that they were working on the same problem. The number of parameters here and the errors. I mean, the errors is just like less than 1%. Like it's a really small margin. But I mean, if you're writing for just making like best performance, if that's what you're supposed to do, just like increase it.
But you know what the difference is between the best like human engineer one and the best performance?
No. I mean, one of the problems, like if you read the paper, like they don't have a lot of analysis. They don't have a lot of analysis to say, oh, we found out this great thing about this one and that one. In the second paper, they show some of the reduction cells that they were able to find out, but they just show it. Like if you look at it, it's like what is so brilliant? Like that, okay, this cell was better than this one, but you can't really connect. Like there's no embedding like knowledge about this. Yeah.
And they discover that it works without cells, they discover.
The second study, I don't know if you were there. The second paper I showed, that was the thing. They used CIFAR-10 and they learned a cell and they took like 12 of these cells and they ran it on ImageNet. More, I think 24 or something. And then it was working better. But not, and the performance was horrible because it still takes a long time to actually learn the extra steps. But in terms of test error, yes, they were able to beat that. And this is like the number of GPUs you need. So they're really proud of this. This you can run on 1080 by itself. Yeah, they're really proud of this. This is the NAS. The first one I talked about, 800 GPUs, 28 days. I was not, sorry. It doesn't matter. And then they have the Smash. A lot of them was actually by Zoff and Baker. They're working on this a lot. And they actually show different times, less than a day. Yeah. This actually is based on one estimate again. If you increase your estimates, then you're going to run into problems. Like this is not going to be. This is based on the fact that you ran one network, you get the reward. Okay, let's talk about conclusion. I already said that m0 = 1 does not converge when you run it. They had the first archive. They mentioned M1. They submitted to ICML. They said it's M1 with 1 works. They had commentators saying that the reviewer is saying this doesn't work. They still publish it with the same M1. Loss of reinforcement in many runs is completely negative, which is also doesn't allow the network to converge. And the moving average baseline that they introduced, they don't really say how they created it, so it actually also doesn't. It's very noisy, the train, in all terms. I actually found 2 implementation of this on PyTorch, and those guys were facing the same issue.
So what does that mean? Most of the reports that there's negative.
I don't know. What does that mean? I don't think it actually makes sense.
But with the view that reinforce makes it worse. So,
Yes.
right. And what was the moving average based on?
Well, what they say is that when they use the reinforced algorithm Williams, they said that the moving average, we use moving average to reduce variance, right? But they don't say how they use it, because then you need the multiplier to know that, okay, we set these ones and it helps to convert. They don't mention it, ever. So you end up experimenting with a lot of these, but then you don't really get anything. It's pretty noisy. So this is the discussions, like, I read this paper, these set of papers, because there was so much talk about AutoML, there was so much talk about Google, like even benchmarks, and call me a fool, but I started reading and I was like, okay, this has to make sense, 3 papers in. And a lot of you on AI Hacks on Saturday saw me like struggling with these papers back and forth. The second paper has a very great section. Zoff says you can read what in the I'm sorry, I didn't hear you.
So you said that random search works as good as reinforcement learning, but is it like almost more?
The performance and the accuracy were almost the same. I don't have the picture because I was scared because I have 557 slides. But yeah, it's very close. Look at the second paper. So it's really, and the second thing is it's really dynamic because you end up saying, okay, the search space should be like have filter heights of 1357. It's just how I mean, you're already embedding priors, you know CFAR, so you probably know what works best. What if you don't know your data? So how flexible is this? I don't think it's really flexible. I think CFAR is such a solved problem, so that you actually end up you not knowing that you're embedding knowledge in the whole problem. So it's not like if you have a data, no one knows what it is. I'm not sure if it's going to work. They also don't actually compare it with like tree parsing estimators. They don't show like, I'm pretty sure with CFAR you actually can get a competitive result just running like 400 trials with just plain tree parsing estimates. Like, they don't really talk about comparison with Bayesian optimization techniques like Gaussian processes. If you look back, all these papers are so new, like 2016, 17. It seems like they invented the field. They're not even looking back at the results we had before. It's like 2016 and 17. This is really strange. So yeah, these were the discussions. So we talked about the reinforced algorithm. We actually criticized using it a bit because it really worked. Is it just like, I mean, if all of you are interested, any of you is interested in reinforcement learning, Google Policy of Truth. There's this article. This guy is actually arguing that policy gradient methods are just random search. They're just like wrapped in mathematical format. It's like, he's just like destroying policy gradient models. He's like super mad. I think so too, actually. In this case, it's not really a framework. It's just like doing some random search thing, especially with M1. If you don't have good estimates. We also talk about neural architecture search. So now you know if someone's like saying this is the solution to all problems, then you have something in your brain to like, talk about. And then we talk about the different variations of this original neural architecture. And there are just more and more papers coming, like genetic algorithms that are like trying really hard to like, this is a new field that are really trying hard to solve. Initially, I just wanted to talk about my implementation. I thought this was going to be super confusing, so I decided to just talk about conclusion. I'm going to release the code soon. Any questions? They as researchers, nerds. This project usually has been Stanford, Google Brain. DeepMind is not working on this. Stanford, Google Brain, I think Facebook. Yes.
about using exponential these problems and maybe they will be faster and people
This is the state of the art. Yeah. They actually mentioned one of these, actually, I can't read, but one of these actually is the work that I think there were like 12 researchers from Stanford did on generative algorithms. And right before this third paper, they were the state of the art. They had like, I don't know, they had like 500 GPUs, not 800. Actually, only in performance. Like major difference. It's like CFAR10. It's not rocket science. Major, it's actually performance. Like if they improve the accuracy, it's been marginal, like 0.2. So that's there is actually more work coming from generative algorithms, mainly from Stanford. But this is the state of the art that I present.
Can you please put up the slide with the references?
Yeah. I'm going to share this presentation as well. But I have quite many slides. Absolutely.
Yeah, so you said that they managed to get lower than
Yes.
do they have some sort of reward for
That's exactly
what is that?
That's exactly the purpose of moving exponential averages. You want to have some sort of like you want to be able to look at past and actually when you get a reward, trying to optimize so you don't have a lot of noise and variance. They don't talk about it. They say we're using something with that baseline, which actually is what you're talking about. Like how are they optimizing the reward to actually narrow it down so that they don't get a lot of variance, so they actually know what they want? I don't know. I actually contacted the authors as well. No one answered. Probably I have to have like at stanford.com so that they answer. Unfortunately, I don't know. But this has to be the baseline.
Thank you very much for the presentation. I'm wondering, it feels like it's stupid that they're training on CFAR because we have to waste too much resources. Do you have any feeling for why they don't take the smaller data sets or simpler data sets to train on? Apply these approaches on those data sets?
I think that when I was in mid 2016, there is a like the same kind of like this space in using W3 tools is like with small data sets. It seems that people want to publish in important conferences and they don't want to use like MNIST or something because they think that it doesn't work. I mean, they could do both, but they don't do it. But CFAR10 in hyperparameter optimization or like these reinforcement learning settings or the meta learning seems to be that everybody's using it. It's like GAN and Celebrity. I don't know. I think it's important to, like you say, limit the problem so that you actually understand what's going on. But they actually have only CFAR10. I mean, in the second, this one, which one? This one. They actually use ImageNet even, which is like 500 GPU, again, story. So I don't know if I can answer, but I think I agree with you. But I don't know why they don't. They want to publish in ICML. The problem, I mean, with Smash, if I'm right, there's already code, like they published the code. So it might be a shorter path depending on how. What I'm saying is like it's revolutionary to you as like individually, go with this because this is the state of the art, at least for image and text data sets. But if you feel like what's the easiest path, I would say use Smash.
When it comes to this replicating single cell, is that also due to AVM sort of research coming up with large networks for imaging, so having one cell that's
I mean,
coming back, replicating one cell that's sort of an architecture that came out at the same time, I guess.
No, actually, the thing is, like, they actually come in sequence. These three papers, they actually come in sequence because they have it's the same author. So Zolf actually started with this NAS, and then after that he started looking at trying to reduce the problem. So he actually came up with this idea of because he works on transfer learning. So he actually tried to made this bold statement: learn a simpler network and just replicate it, and it probably worked for him. That's why he published a second paper here. And then the third paper, there were other people using this idea, but in a very strange setting, both CFAR 10. Do I make sense? Did I answer your question? Or?
Yeah. I mean, because you say that some of the other like high-performing networks, they would use the same approach.
Yes,
But maybe that was before this restriction.
Yes.
I mean, I don't know who was influencing who.
I
assume it's
That's a good question.
I don't know.
That's a good question. I myself just followed the historical line here. Like started with the first one till the third one. But like many references. Looks like the time.
Implementation, where did you start?
Where did I start? I started looking at the PyTorch implementation. It's like halfway done. Doesn't work for. I was not interested in the RNN example. They only implemented the RNN example. Then I contacted the guy, just like talked to him. He said I haven't been able to reproduce. Then he showed me 2 forks. Then I looked at the forks, and then I ran them. Also didn't get the accuracy. Got disappointed. I was like, I need to start myself. But I did not do it with PyTorch. I did it with TensorFlow. Thank you.
Thank you. So now we're going to have a break for 15-20 minutes, and then we're going to get some food. But I also wanted you to maybe have a little grupparbete, as it is in Swedish, because I think it's really nice. There's so many people here, and also a lot of new faces. So this event is part of AI Week, and it's organized by Stockholm AI, which is a non-profit we're working with in Stockholm. And the questions I want to think about is related to how we can make the community for people working in machine learning and data science better. So the questions are, what events do you want more of related to machine learning and data science? What do you want to learn more about in machine learning, and how can you build better communities in machine learning in Stockholm? So while you're eating food, maybe you can talk to someone you haven't met before and discuss these things. And then you can come to me something about it later, or just raise your hand and say something. Okay, thank you. Thank you. The food's going to come here, so you can just stay. Or if you want to go.